Greetings. In this video, we are going to go through the 2D geostatistics tutorial with GMS. And up until now, um, we have been building several mod flow models. And for the top and bottom elevations for the grid layers for these models, we've just been using constant values, resulting in like a flat grid. Well, in reality, nothing's perfectly flat. And so it's more common to take measurements at a variety of points and then interpolate them to get a more realistic definition of your grid elevations. And for the ground surface, this is often done using digital elevation model data, which is available from a number of sources. And then for the lower layers, you can take pics off of boreholes or data implied from geologic maps, etc., and interpolate it. And in some cases, you interpolate other things as well. You could have discrete measurements of hydraulic conductivity, for example, that you wish to interpolate over a grid. And we're going to see that later when we do pilot point interpolation to set up hydraulic conductivity as part of a calibration process. And so, to support this variety of applications, GMS has a 2D scatter point module, and you can do geostatistics. Geostatistics is a term that's frequently used to describe 2- and 3-dimensional interpolation from limited data using geoscience data. It was originally developed and expanded in the mining industry. And we'll look at some of the algorithms that were implemented. GMS supports a variety of interpolation techniques, and so we'll go through that and look at how the 2D scatter point module works in GMS. So I'm going to push this to the side for a second, and basically what we're doing, I'm going to bring up the Alcoveo GMS tutorial website. And if you click on, they have tabs up here. There's a large number of mod flow tutorials, mod flow related tutorials, just some generic tools in GMS, and then a few non-mod flow tutorials as well. But in the GMS tab over here, there's a tutorial for 2D geostatistics and 3D geostatistics. And so for this tutorial, there's a PDF file that I just had. It's this file right here that gives you step-by-step instructions, and I've downloaded that. There's also a zip archive that if you download it and unzip it, you get this set of files here. There's a plume.txt file, ellipse2g.dat, and a sample file. And so we'll be importing this data into GMS as we move along with our tutorial exercise. And so here we are in GMS. This is the 2D scatter point module right here, and it has a pretty limited set of tools. There's one to select scatter points, one to select a particular scatter point set, and one to create scatter points. And so you can actually go in and just start clicking to create scatter points, and it creates a default scatter point set over here. And as I select these scatter points, I can edit their values. Let's see, I need to turn on, it says lock. If I turn that off, the lock option in the scatter point module, then I can edit them, and I can drag them to a new location. I can type in an XY coordinate, I can type in an elevation, and I can type in a data set value. Now, one of the features here with scatter point data, I can have multiple scatter point sets. So if I click here and say, let's see, new 2D scatter point set, it basically creates a new one. I can rename that to be my set, and since it's the active scatter point set, now if I start clicking And I'm creating a second set of scatter points. And I can, you know, toggle the display of these on and off. They kind of look the same, but it's possible if you go into the scatter point set options, you can pick different colors and symbols for each of these. And so, for example, you might have one scatter point set representing your top elevations and another one representing your bottom elevations because they're sampled at different XY locations, and one might be really dense and another one might be very sparse. And then for each scatter point set, you can have multiple data sets, and a data set is like a field in the sense of if you're familiar with how 2D point feature classes work in, say, in the GIS world, something like ArcGIS. You could have one field representing maybe for a particular set of locations, you could have one for the top elevation, one for the bottom elevation, or one for hydraulic conductivity and one for the storage coefficient or something. Assuming they're sampled at the same locations, you can pile up, you can have multiple arrays essentially representing different data set values. And so we'll see some of that as we go along. Now, normally you don't interactively create your own scatter point sets. Typically you import them and then do interpolation based on that. So I'm just going to wipe out what we did here, and we're going to import a scatter point set. We're going to do File Open, and I'm going to go into this GOS 2D folder, which I created by unzipping the archive, the zip file that we downloaded. And I'm going to change the filter here to all files, and there is a plume dat.txt file. Now, by the way, before I go through this process, I just want to show you what that represents. So this is just a flat text file, and it has, I've got it open here in Notepad, and it has 4 different columns of data. There's tab delimited. The first one is an ID, the second one is an X coordinate, and then a Y coordinate, and then C is a concentration value. So we've got the first row up here is kind of a header row, and then the rest of these are just simple rows and columns. Now, this is something that you could just prepare in a text editor, or you could do it in a Excel or Google Sheets and then save that as a text file. In fact, you can do the same process by copying and pasting from Excel using the Windows clipboard and do the same thing. But the point is, you just need some data in this simple format here. The ID column is optional. If you omit that, it just numbers them sequentially, like is shown here. You can also give text names for these as well if you don't want to use numbers. And but the X, Y columns are required, and then you can have one or more data set columns. This one we only have one, but you can have multiple data set columns. Now notice most of these C values in this last column are 0. We'll come back to that later. But so basically we've opened that file, and it's showing it here. This particular dialog is very similar to the text import dialog that you'll see in Microsoft Excel. We're telling it to start importing at row 1, but we're also telling it that we have a heading row. So the first row there is treated differently when you toggle that on. And then you can click on what delimiters that it uses. This is tab delimited, so we have that on, and you'll see these lines here show how it's interpreted the columns, and that looks correct. So we'll go to the next tab, and here we have to say, okay, what are you importing this into? And there are a lot of different things, types of objects in GMS where we can import from a text file. So we have to tell it what we're doing. These are 2D scatter points. So we select that, and then it says, and now what the next step is to tell it what each of these columns represent. Now, the reason it does this is it would allow you to have your data in whatever columns you want. So it adds some flexibility. We just have to tell it where the columns are. So it's looking, so you do this top row here, there's a little pull down, and we can say, okay, this first column is the label field, is what we call this. It's just an optional identifier. And the second column is X. It's automatically picked the X column, and then we've got the Y column. It's detected that automatically. And then the last one, we're saying, well, this is just a generic data set. And again, you can have multiple data sets, but this will work out. And then you can give it a name. This is the name of the scatter point set. We'll just leave it at Plume, P-L-U-M-E-D-A-T, and we'll click Finish. And there is our scatter point set imported to GMS. And now I'm going to do File Save As, and I'll just save that as plumedat.gpr. That would be fine. And now let's play with some display options. There is a set of display options for 2D scatter point data. We are going to turn on, let's see, we want to do scatter point symbols. We can also turn on contours. Now, what does it mean to have contours in for scatter points? It basically means it's going to color code each of these scatter points based on their values, their data set values. And so it ranges from a high of 99 to a low of 0. And if I go up here to my contour options, let's see, color ramp, I'm going to reverse this color ramp and see what that does for me. Okay, now I've got the high values, which are around 100, are red or hot, and the low values are blue. And a lot of these are 0. And so there's some other things you can do. You can turn on a little values tag, and it will display a number next to each point representing the data set value that it has. So that's kind of nice. So you can see we have 98.4 in the middle, 90. So we have this region in the middle where we have non-zero values, and then once you get out to a certain distance, they turn into 0 values. So again, the use case here is we have like a contaminant plume in the groundwater, and these are the relative concentrations from 0 to a maximum of 100, implying 100%, the concentrated product in the groundwater. It's pretty unlikely you'd have something that high, but it's just a hypothetical example. And so what we want to do now is interpolate from these values to a grid so that we can generate a contour map and maybe a 2D surface plot. And so to do that, we're going to go over to our scatter point object here in the Project Explorer window. We're going to right click and say Bounding 2D Grid. And what that does, let's see, we're going to do 60 cells in X and 40 cells in Y. And click OK. Let's see, click OK now. And let's frame that a little bit. And what we've done is it creates a 2D grid with the number of rows and columns that we've defined, and it extends it just beyond the limits of our scatter point set. And so now we have something we can interpolate to. So let's save our changes, and to interpolate, there's an interpolation menu, and there's an interpolation options dialog, and we have a number of different interpolation methods that we can use here: linear, inverse distance weighted, Cleft-Toscher, natural neighbor, and Kriging. And then log interpolation, anisotropy, and some other things. We're going to select linear interpolation. And by the way, if you had multiple scatter point sets and multiple data sets, it would let you pick from which scatter point set do you want to interpolate and which data set you want to use. We only have one scatter point set and one data set, so those are dimmed right now. Keep things simple. So we're going to start out with linear interpolation, which is really simple. And we'll go back to the interpolation menu. You notice there are a lot of things we can interpolate to. We can interpolate to a tin, a triangulated irregular network, to a 2D finite element mesh, 2D grid, 3D mesh, 3D grid, mod flow layers. We'll come back to that layer later and talk about that. But the only one that's undimmed right now is a 2D grid, because that's the only other object we have in memory, and that's what we want to do. So we'll select OK. And now, before we do it, interpolating to the 2D grid is going to create a new data set. Now, when you have a data set on a grid, it's kind of like a raster. And if you look at the data set over the 2D grid over here, it has a default data set, which is just its elevation. And so this interpolation will create a new data set. And so we're going to give it a name. And it says C underscore linear. C is our data set name, and linear is the option. So it uses a little bit of intelligence to come up with a suggested name, and that one looks fine. We're going to just click OK. And when we do that, you will see a set of contours appear. And we have let's see, let me change the display options just for a minute. We'll turn off those cell edges and maybe turn on a grid boundary. So there's you can see our contours a little better there. And so that's what happens when you interpolate. It defines a kind of a surface that interpolates those points and kind of fills in the gaps between those points and even does a little bit of extrapolation. So if we were to, another thing you can do with this is you can go into 3D view. So if I switch to oblique view here, so again, you can do top view or oblique view, and once I'm in oblique view, I can actually, using this tool right here, right under the magnifying glass, the rotate tool, I can begin to rotate that around. We just have kind of wireframe contours at this point, but if we go into our display options, and we can turn our cell edges back on, and you can kind of see the shape of that surface as you spin it around. You can also turn on cell faces, and that will it just kind of fills them in with a constant color here. I'm not sure that's terribly useful in this context. You can also turn on, if you go into the contour options, you can do this color fill and linear contour option here. And now we're talking. This is my favorite way to look at it. So now we can get a much better 3D view. I believe we could even turn the cell edges off now if we wanted to and just get the smooth contours there. So now you can kind of see the shape of this. It kind of looks like a mountain that we're rotating around. You can see from the bottom there's a little hole, or kind of like a hat or a sombrero or something. And again, so it's trying to recreate, it's interpolating those points and trying to generate a surface that does a reasonable interpolation of that. Now, linear contouring kind of does what the name implies. It actually, what it does, first of all, is it triangulates these points, so it connects them with a series of triangles. The triangles aren't actually shown, but you can see from the shape of the contours where those triangles are, basically. And so, and then it just linearly interpolates across the face of each of those planar triangles. So that's one of the interpolation options we have. And at this point, though, you know, what are we shooting for? What is the true answer here? And in most cases, you don't know that. You're just doing the best you can from the limited data that you have. But in this case, we've actually there's actually an answer to this. So I'm going to go up to the 2D grid module, and I'm going to say, let's see, where is my command? Import. I need to import data set. There it is. I right click on the grid and do import data set. I'm going to, it imported from a file a data set called control function. So this, and now you can see it here. So this, these points, the values that we generated were actually derived mathematically from this elliptical surface. And it goes out to a certain point and then it's 0. Now if you're looking at this in plan view, what this is meant to represent is a contaminant plume that's moving, for example, from west to east or east to west in our aquifer. And when that happens, you generally do get contours like this that are in this elliptical shape. And so the idea here is we've sampled the groundwater at these locations, and a lot of them are 0, but here inside this plume you have different values. And so let me go back to oblique view for a second. This is the reason we've done it this way is we know what the true solution would look like. It should look like this, and this will help us interpret how accurate these interpolation methods are. So this is, now by the way, if I go over here to the 2D grid and I click on the different data sets, it loads that and just changes the display. So I can kind of toggle back and forth. So this is a true answer, and this is our best guess using linear interpolation. Okay, so let's save our changes, and we're going to try another interpolation technique. And we're going to go here to the scatter point module, select interpolation options, and this time we're going to do inverse distance weighted interpolation, and it has a number of options. We're going to start with one called Shepard's method, and we'll click OK and exit that, and we'll say interpolate to 2D grid, and gives us a name for that. And there we go. Let's look at this in oblique view. So this is IDW interpolation is actually something that's fairly common. Now, by the way, I'm gonna reverse that color ramp, so we get red being whoops. Got to do it on the grid. Here we go. Color ramp, reverse. There we go. Now red is maximum. So this is what we wanted to see, with red being hot and blue being cool. So yeah, as we switch back and forth between the control function, you can see again it gets the general shape. So here's IDW, here's linear. It does a decent job of representing that. One of the things you'll see with IDW interpolation is these little bumps. It tends to, and by the way, all of these techniques, if you look at the surface exactly at the point, it will precisely pass through that point, and then kind of approximate it at best it can in between. So a feature of IDW interpolation is it passes through each point, but then it kind of tends toward the average between the points. So you tend to get these little bumps, and down at the bottom you get little valleys. And yeah, it's okay, but not great. But there are other variations on IDW. There's, whoops, wrong window. I'm going to go to the scatter point module, interpolation options, and for example, there's a method called gradient plane. So what it does is it fits a planar surface to each of the points using least squares regression, and then it blends those planar surfaces instead of just averaging the value at each point. So it tends to give you a little bit smoother interpolation. And so IDW gradient, and there you go. So that's what we get with IDW gradient plane interpolation. And if you look in plan view now, the middle of this is starting to again look more similar to our control function. One of the problems we have, however, is yeah, so look at this region out here. So we got a series of points here that are 0. And what happens, let me put it in 3D view and rotate it. Whoops, let me rotate that around. So, whoops, I've got some selected cells. Let me unselect the cells. And so you'll see what it does is it looks at the trend in the surface right here, and it just keeps projecting it downward. If we had another scatter point out here at 0, it wouldn't do that, but it projects them downward. So that's one of the issues you have to be careful with. And there's a way to deal with that. You can go in to the whoops, wrong thing again, to the interpolation options, and there's a way to truncate values. Truncate to the max min of the data set, truncate to a specified range. We know that our max is going to be 100 and our min should be 0, so we'll say, okay, if you have anything over 100 and anything less than 0, just clip it to that range. And so now if we use that same, I'm going to add on truncated here to the name. And so now what it does is it doesn't make any difference on the high end, but on the low end, anything that's less than 0, it makes it 0. So now this does a much better job. So now that's a pretty good solution. That looks, if you compare that to the control function, we're getting a lot better. There's another version of IDW. It's called quadratic interpolation. That tends to make things even a little smoother. Instead of fitting a plane to each point, it fits a quadratic function and then blends those together. So let's see what that looks like. IDW quad underscore trunk. We're still truncating. And yeah, as you can see there, that there's a little bit of an upswing out here. It goes down and then back up, which is a little problematic in this case. We could fix that by putting some more points over there. But you know, if you look at this in plan view now and compare that to the control function, you know, it's pretty good. So there's quadratic, there's the gradient plane, and there's the control function. Another thing you can do to change this a little bit is put in an anisotropy. Now it's clear that the control function is kind of blended, biased in the horizontal direction. So if we go into the interpolation options, there's a way to define anisotropy. So if we go here and we say the default anisotropy factor is 1, but I'm going to change that to 2. And then there's an azimuth. This is an angle, and I'm going to change that to 90 degrees. And this combination of numbers, what it does is it will ensure that the interpolation is biased to prefer the horizontal direction. And I'm going to click OK. And essentially what it does is it from 90 degrees from the x-axis, which is vertical, it stretches the x distance by a factor of 2. And what that does is it makes the things in the horizontal direction appear relatively closer when you do the interpolation. So now let's say interpolate to grid, trunk, and then I'll say anis 2 for anisotropy, and there you go. So this is without anisotropy, and this is with anisotropy equal to 1, and this is anisotropy equal to 2. So again, you get a pretty nice solution there in the middle. So that's another thing you can do. Okay, finally, the last but certainly not least, we're going to skip a, um, let's see, what are we going to skip? We are skipping the Cleft-Toscher natural neighbor. We're going to jump right to Kriging. Kriging is a really well-known, um, probably the most well-known interpolation technique. And there's pretty good argument that it's the most accurate. And so why don't we just use Kriging all the time? Well, unfortunately, Kriging requires some pre-processing. It's not always. I mean, there are ways you can automate it, but it does require some analysis before you use it. And so we're going to go into the Kriging options, and we have to define something called the variogram. And we have to, first of all, we're going to generate an experimental variogram. And it has some options here that we can set up. We'll click OK. And basically what a variogram is it takes each point and it compares it to all the other points as a function of distance. And it determines how much the data set value varies as a function of separation distance between the points. And so if the points are really close together, they're not going to vary at all. Or maybe sometimes there's a little bit of noise here, which we call the nugget. And as the farther you go away, the bigger the average variance between the data values. Now, in a typical variogram, this will increase linearly or spherically, then it'll get out to a point, and then it just kind of flattens out. In other words, once you get over a certain separation distance away or between the points, there's just kind of an average variance between the values, and that average out here is called the contribution. Sometimes it's called the sill. And then the distance that you have to go before you hit that flat part is called the range. So that's the range over which the points are kind of correlated. Now, we have a kind of a unique case here because a lot of our values are 0. So once you get, so this variogram goes up and then it goes down, and that's a little bit deceptive. It applies, well, the farther you get apart, the more similar the points are. Well, that's only because we have a whole bunch of 0 values. So that's kind of a special case. So then, once you generate your experimental variogram, the next step is to create a model variogram, which is also called a nested structure. And if you click New here, it will create that, and then you can use these little sliders to adjust the range and the contribution. So what you're trying to do is come up with a mathematical definition of a variogram here that fits your experimental variogram. So your experimental variogram is kind of the model data, and the red line here is kind of your best fit to it. Now, hey, this goes down. Why doesn't the red line go down? Well, they don't do that. It just goes up, and it has to go straight at some point. And there are different kinds of variograms you can fit. Gaussian. No, that one's actually not bad. Maybe we'll keep that one around. And anyway, once you get a fit you're happy with, you click OK. And we're going to continue to truncate. The anisotropy doesn't apply here. It has its own kind of anisotropy. And then we will say interpolate to 2D grid. And there you have it. So again, let's compare that to our control function. A little bit expanded out. By the way, you can play with this by I'm going to go into the interpolation options, and I'm going to go back to the variogram, and I'm going to give it a smaller range. Let's see, slide that back to here, for example. And we'll click OK. And then we'll do this again just to show you what the range does. We'll call this Krig 2. And so here we go. Here's the default range we started with, and here's the second range. So you can change the shape, tighten up this interpolation a little bit, if you will, by playing with that range. And so This is a good view to look at. So now if you look at the control function, here's the control function, here's Kriging. You know, the shape of this thing in the middle is really accurate. Now we get these undulations out here, which are regions where we don't have data, and we can, there are ways to deal with that. But anyway, so overall, Kriging is a really good technique that gives us a really good interpolation of this surface, but you know, you do have to do some things to set it up, which can be a little bit time consuming. That's why we don't make it the default value. All right, one last thing I want to show you is in the, if you go to the 2D grid module, and there is a data set calculator in the edit menu. We've got all these data sets here. If we wanted to see the difference between the two Kriging solutions, they are data sets are numbered D1 through D10. So if we want to do the difference between D10 and D12, we could say, put a little expression here, absolute value D10 minus D12, and we'll call this Krig diff. So the idea here is you can write these mathematical expressions to do computations between different data sets. And so we're going to do that and hit compute and click OK. So this new data set we created is the mathematical difference between this solution and this solution. Okay, and it's also scaled, and so that's kind of interesting. So that allows you to do like raster algebra, if you will, to look at differences between data sets on your 2D grid. Anyway, so that is a very quick rundown of 2D scatter points. There are a lot more we could say about it, but that gives you a flavor. Very easy to use. Just import your points and create a grid and start interpolating and playing with that, and you can really have some fun with this and do some powerful things. And later in one of our other cases, we're going to show you how you can use this to interpolate directly to the layers of a mod flow grid to define your top and bottom elevations.